In this video lecture, we're going to be talking about Java sockets. If you want some good notes on it, you should go to see the Java tutorial, which you can find by going to my 365 website and going to the Java sockets link. We're going to be talking about a number of topics with sockets. So we're going to start out with a quick review of what are sockets, then show you the typical client-server interaction with sockets. Then we're going to go through a number of examples, starting with a simple single client-server example where we're just echoing back whatever the server sends us. Then we're going to talk about how you can add in synchronized data objects so that you can handle multiple threads or multiple clients. Then we'll be moving on to multi-threaded servers that handle multiple clients and multi-threaded clients. And finally, we'll talk about how to detect client and server shutdown so that you can exit gracefully. A socket is simply the endpoint of a two-way communication link between two programs running on the network. They're typically running on different machines and they need to communicate in some way. One of these processes for this course will be called the server and one is called the client. You can see in this diagram that the server is listening on a port and the client is going to request a connection by providing the server's IP address, which typically will be a host name, and the port number that the server is listening on. When that connection request comes in, the server will accept the connection and then establish a two-way connection between the server and the client. And the way that's done is that each of them gets a socket on their machine. And the client's port will not be the same number as the server's port. The port is an integer between 0 and some arbitrarily big number. Typically on the server side, it will be listening to a port greater than 5,000 simply because there are system-provided programs whose port numbers are less than 5,000. When the connection is established, the client is assigned a local port number. It will be different than the server port number. And if I establish two running programs on the same client, for example, two chat programs on the same client, they would have different local port numbers. This slide shows the typical interaction between a server and a client. The server begins by creating a new socket, by creating a new socket server object, and we'll talk about that in a moment. The client then establishes a connection by creating a new socket in its program. That will make an access request to the server, and the server has a method called accept, or the socket server has a method called accept that accepts it, and at that point a socket gets created for the client, one socket on the server and one socket on the client, each listening on an appropriate port. And each of those sockets has a write stream and a read stream. So on the client will write to its stream, and when it does so, any output from that write stream is put into the read stream for the server. The server can now read from that stream, do some processing, and typically will then write into its output stream. That output stream in turn writes into the client's read stream. The client will typically do some processing and often will print that output to either standard out or, if it's a graphical interface, to the graphical interface. And conversely, the client is typically getting input either from standard in or from a graphical user interface, and it is putting that information into its write stream. At some point, either the server shuts down with a close or the client shuts down with a close. In both cases, what you need to do is shut down the streams first and then shut down the sockets. We're now going to move on to a simple client-server example. And we're going to be looking at the Echo client that the Java socket tutorial talks about. Now, one thing we need to mention is you're going to see something called try with resources, and it's only working for Java version 1.7 or later. Our Hydra machines as of April 2014 are running Java 1.6 and hence don't support this newest try construct. So you'll have to use the old construct, not the one you're about to see on the Java pages. I'm first going to simply run the Echo server and the Echo client so you can get an idea of the interaction. You can see that what I've done is started a Echo server on Hydra 4, and it's going to be listening on port 6000. And on Hydra 10, I have launched the Echo client, giving it as parameters the host name of the server, Hydra 4, and the port name 6000. Now if I start typing in things, it's simply going to echo them back. And over here, if I ultimately hit Control C, it goes away. You'll notice that it does not initially go away over here, but if I try to enter one more thing, now it goes away. And we will talk about how to do that later in this lecture. Let's take a look at the critical parts of the Echo client first. As you can see, we first start getting the host name and the port number, and then we're doing our try. And this is what I was talking about a moment ago with the try with resources. You'll see that there's parentheses. And what that does is that when the try is about to exit, it automatically closes these resources, the Echo socket and the input and output streams. And furthermore, it makes sure that the input streams are closed before the socket stream. You will not be able to do that. You will have to explicitly write the old try statement and then put your closes in. And I'll show you how to do that in a moment. But first, we'll just show you how to do it with Java version 7. So we first are creating a new socket and establishing the connection with the host name. If for some reason it doesn't work, we would get an exception. But in this case, it works, and we are allocated a socket. And now that socket has an output stream, which we are going to wrap into a print writer object to make it easier to write to it. And it also comes with an input stream. If you remember, that's what we're going to be reading from the server. Whatever is in our input stream is coming from the server, whereas whatever is in our output stream is going to the server. And we put that into a buffered reader. Now this will let us read a single line of input, which is what all we need to do for this application. If we needed to break that line into parts, then we would also have to wrap the line that we input into a scanner object. And finally, we're also going to be reading from standard in, and so we wrap system in also into a buffered reader, so we'll be able to do that. And this is typical of all clients when they start up. They're going to try to establish a connection. They'll get a socket. Then you'll typically need to put the output and input streams into suitable objects for printing and reading, and then you may also need to do something with standard in. Here's the basic logic now, and you can see that what we're doing is getting input from the user via standard in. And as long as we haven't had a Control-C or a Control-D to interrupt us, we will print whatever the user has input to our output stream. And remember, that is going to be writing to the server, and the server will be reading it from its input stream. Then, whatever we get back from the server, which is going to be in our input stream, we will read using readLine and preface it with echo. When we eventually hit Control-C, we will stop this process and exit. This kind of gives you, here at the bottom, the general idea of what the client typically does. Opens a socket, gets the input and output streams to the socket, then it's going to read from and write to the stream and do whatever processing it needs to do. Then it'll close the streams and close the socket. What you see now is the modifications I made to the code to make it work on Hydra. So you can first see that I have declared the 4 variables, echo socket, and then the 3 input and output streams outside the try block, and I've set them all to null. Then inside the try block, I've written it the old-fashioned way, and I've created instances of each of them. At the bottom, you'll see that there is a finally clause that's going to handle or be executed no matter what. And you see that I closed these streams in the reverse order that I created them, and then I close the echo socket. You also notice I need to make sure that they're not null, or else I may get some complaints from the Java compiler. And then you can see that there are some catches down here as well. If I tried to create a socket and it gave the wrong name, I'd get an unknown host exception. I also can get I/O exceptions when I read or write, and so I need to also catch those exceptions, in which case I would immediately exit from the program. Now let's take a quick look at the Echo server. It's very simple. It takes a single argument, which is going to be our port number, and it's going to simply get that port number, and then you see that it creates a server socket with the specified port number. Then it simply waits for a client to try to make a connection, and when it does, the accept command will unblock. So the accept command will block waiting for a client. When the client makes a connection, accept will unblock and we'll get a client socket back. Now this is not the same socket that the Echo client got. This is a socket that is on the server side. Again, we get our output and input streams. Remember, the output stream is now what is going back to the client, and our input stream is what's coming in from the client. So what we're going to do is simply get into an infinite loop where we are reading what the client has sent us, and then we're simply dumping it back to the client. And if the client ever exits, then it will immediately send a null value. Read line will read that null value, and we will fall out of the loop. And in this case, because we only have a single client, we will exit the server. Now we're going to move on to more complicated examples, which is where you may have multiple clients and or you have to do some processing. Typically, you do not want to do the processing in the thread that's accepting connections because you need it to be a tight loop. You don't want the potential client sitting there while you potentially do a data-intensive operation. Therefore, we typically create a data object which is going to do whatever processing we need to do. And furthermore, we're typically going to be forking off some threads, server-side threads, one thread for each client that will be dealing with this data object. We'll get to that thread creation in a moment. We're first going to illustrate this data object protocol in action with the next example from the Java socket tutorial, where they use the so-called knock-knock server. So in this case, what's happening is there is a server that is serving up knock-knock jokes. And the client is basically waiting on it and being sent clues. Let's first take a look at what the two things do. So on the Hydra 4 machine, I have launched the knock-knock server, and it's listening on port 7500. And on Hydra 10, I have launched a knock knock client, and it has given the host name Hydra 4 and the port number. And you can see that knock knock server has accepted the client connection and sent the first item, which is knock knock. And now we're supposed to say who's there. And the server says turnip. And now we're supposed to say turnip who. And the server says turn up the heat, it's cold in here, want another. And we're going to say yes. And now I'm going to incorrectly answer, so I'm going to say who. And it says you're supposed to say who's there. Try again, so we will. Okay, and now we're supposed to say little old lady who, but I'll just say little who. And it says you're supposed to say little old lady who, try again, knock knock. So I have to go through the whole sequence then. Who's there? Little old lady who. I didn't know you could yodel. And now I say no. And you can see that both the client terminated and the server terminated. So the knock knock server uses a data object that it calls knock knock protocol. And essentially, this data object implements a finite state machine. It starts in a state called waiting, and it has the state for when the knock knock's been sent, the state when it sent the clue, such as turnip, and then if you give the right response, it serves the answer and asks you if you want another. So we start out in the waiting state, and from the waiting state, as soon as the client establishes a connection, we unconditionally serve the knock knock string, bringing us to the sent knock knock state. We then are waiting, and the user is either going to type who's there, or they're going to type something other than who's there. If they type who's there, we're going to serve with the clue, such as turnip, and go to sent clue. If they type in something incorrect, we're going to return to the sent knock knock state and send the client the knock knock string again. From the sent clue state, if the user again matches the clue with the word who, such as turnip who, we serve them an answer and also ask them if they want another and proceed to the another state. If they don't give us the clue with who, which is right here, then we serve them knock knock as well as telling them to try again and head back to the sent knock knock state. Finally, from the another state, we're going to ask them whether they want another or not. In fact, that's what got served. If the answer says no, we send the client the word bye and go back to the waiting state. And if they say yes, then we serve up another knock knock string and go back to the sent knock knock state. Now actually, even though we go to the waiting state, the server is going to end up terminating at this point. However, for completeness, the example does proceed back to the waiting state. So again, we're going to look at the code for both the client and the server, plus the data protocol object, which is the knock knock finite state machine. So the server is doing the same thing it did in the Echo server example. It's getting a server socket with the appropriate port number. Then it's waiting for a client to attach itself, and when it does, it gets a client socket, and then it sets up its input and output streams. Next, it goes into the heart of the logic, which is that it sets up this finite state machine, which is in the knock knock protocol object, and it starts by simply sending null to process input, and that's going to give us the line that we're supposed to serve to the client. Remember that unconditionally it's going to make a transition from the waiting state to the sent knock knock state, and the output line is going to be knock knock. So at this point we will send that knock knock line to the client. We now enter a loop where we're waiting for the response from the client. When we get the response, we pass that response to our knock knock protocol object, and it's going to make the appropriate transition and give us an output line back. We serve that line back to the client, and then if the output line is by, we break. Breaking out of the while loop is going to cause the server to terminate. Here you can see the knock knock protocol, and you can see that it has the 4 states that we showed you in the PowerPoint slide. It has a limit on the jokes before it cycles around to the beginning. Then it says the initial state is waiting, the initial joke is 0. Then it has the set of clues and the set of answers to those clues. Then it simply implements the state machine. So for example, if the state is waiting, it unconditionally sets the output to knock knock and sets the state to sent knock knock. If it's in the state sent knock knock and it gets a valid response from the user, then the output it creates is the appropriate clue, and it sets the state to sent clue. Otherwise, it gives the user an error message and says to try again with, and says knock knock. Okay, and in this case, the state stays as sent knock knock. And you can trace through the rest of your code yourself. At the end, it returns the output string. Finally, the knock knock client simply tries to make a connection by calling socket with both the host name and the port number. When the server accepts it, then a socket object is created on the client side. It again gets the output stream, which is what it will be writing to the server, and the input stream, which is what the server is sending to it. And then it enters its main loop. And what it's doing is it's going to be reading from the server, and if it gets a null line from the server has shut down for some reason, so it needs to get out. Otherwise, it prints whatever the server sent us and notes that it's from the server. If the server is telling us that it is shutting down by giving us bye, then we break. And you may say, well, wait a minute, what about this null? That's if we prematurely terminate the server with a Control-C or Control-D. Then we're going to get input from the user, from the console. Now there's actually a bit of a bug here in this logic, which is if we get a Control-D from the user, that's going to close the standard in, and it's going to cause null to be coming into our program. And in that case, we're not going to do anything, but we're going to continue in our while loop. And it turns out at this point, we are going to be in a deadlock situation because the server is waiting for us to send it something. So it's sitting there waiting to read from our read line. It's going to be up here waiting for us to send it something. We are going to be down here also waiting for it to send us something. So in fact, this should not really be from user not equal null. It's okay if that's not equal null, but then there needs to be a break that's going to get us out of here so that the server knows that we are terminating and the server can shut down as well. So you can try this yourself with the knock knock server. If you hit Control-D, it will close the standard in, but then neither the client nor the server shuts down. If we did get some valid data from the user, then we send it to the, or we print it out first, and then we send it to the server, and the server is going to process it, and we'll go up and wait for the server's response. Now, it's relatively rare that we have a server dedicated to a single client. In fact, we typically have a server that's going to accept connections from multiple clients. And therefore, we have to set up the server so that it is multi-threaded. And we're going to next look at an example by looking at the multi-threaded knock-knock example. In order to implement the multi-threaded knock-knock server, we have to divide the server into two classes. The first class, the multi-server, is going to be simply handling connections and is going to be forking off threads, one for each incoming client. So you can see down here, what we're going to do is get a new server socket, and then we're going to go into an infinite loop. Listening is set to true. And you can see that what we're doing is we are waiting for a connection from the client, which is what we're doing right here. When we get it, we get a socket back, a client socket, and we're immediately forking off a new server thread to handle that client. You'll notice we're not doing any other processing in this loop. This needs to be a very tight loop because we don't want other clients having to wait if we sit here trying to, for example, handle multiple clients and do all the processing. So instead, we immediately create a thread to deal with the client and go back to listening for connections. Here you see the server thread that's handling the multiple knock-knock server clients. So it is getting the client socket in the constructor and it saves that socket. Then in the run command, it does what previously was done by the main server thread, which is it gets the output stream that it's going to be using to write to the client and the input stream that it's going to be using to get input from the client. Now in this case, each client gets its own dedicated knock-knock protocol object because there's no conflict. Each of them wants to be getting jokes and not having them interleaved with someone else's jokes. So for each client, we create a new knock-knock object that keeps track of the information for that client. And then the rest of it is just like the logic that you saw before, and I'm not going to repeat it here. You will see at the very end that we do close the socket, and that's because the try with resources was no longer going to be able to close the socket because it was created in the main thread. So here we have to explicitly shut down the client socket when we exit. Now going back to the multi-server for a moment, you will also notice that it does not exit when a client thread is finished. Before, when there was only one client and we handled that client, when the client exited, we returned. But here you can see we're spinning in an infinite loop. And the only way we're actually going to shut down is if we hit Control-C on the console window and actually kill off the server. Now just going back to our synchronized data objects for a moment, with the knock-knock server, it wasn't necessary to have a shared data object, but oftentimes we do have to have a synchronized data object. The obvious example is when the server has a database, such as with Amazon or eBay, and the clients are all needing to access that database. In that case, the database software does the synchronization for you. However, let's say that you were implementing a chat program. In that case, you would have shared data because as the clients entered a chat room, they would be sending lines from the chat room to the server, and the server is going to have different threads for each client. And now each of those threads, server threads, is going to be potentially accessing the data object that is keeping track of the chat room lines. And you need to make sure that only one server thread has access to this data object at any one time. So if two different clients send lines from the chat room simultaneously, you need to make sure the data object is synchronized so that one of those server threads is able to put its line to the data object. The other server thread has to wait until the first server thread is done, and then it can also put its line to the data object. Now, there also may be a need to multi-thread the client, and this is going to happen in a chat room where you're going to be getting input from the user, but you're also going to be getting input from the server, and you need to be listening to both of these streams simultaneously. You need to be listening to standard in because whenever the user types in a message, you need to send that to the server via the write stream, but you also need to be listening to the read stream that's coming in from the server, because if any other client has typed in a line, you need to be able to put that to standard out. Well, you can't be listening to two input streams simultaneously. The reason is that when you listen to an input stream, you block. So if I try to listen to standard in, I'm going to be blocked on standard in, and I won't be able to get any messages that are coming in from other people. So to handle this problem, I'm going to have to fork at least one thread. You could fork two, but minimally you need to fork one. So in this example, I'm letting the main thread continue to handle standard in. So when it gets something from standard in, it puts it into the write stream and sends it to the server. But I fork off a separate thread on the client side that's going to be listening to the server's thread, or going to be listening to the input from the server. And when it gets input, it's going to put that input to standard out. And you will need to do that in your JTalk lab that has been assigned. Here's the pseudocode for a multi-threaded client. This is pseudocode that you can use for creating a chat room. You would, again, in the main thread, create the new socket. Then you would get the socket read and socket write objects, so the buffered reader and the print writer. Now you're going to create a write console thread that's going to be passed the socket read object, so that write console thread can sit on the sockets stream, and when the socket sends information, it can write it. Then we simply go into our while loop, and while there's more data coming from standard in, we process it, and then we write that processed information to the socket write object, which will send it to the server. The write console thread simply goes into a loop where it's waiting on the socket to send it information. When it gets it, it does whatever processing is required and then writes that line to the console. The final thing we have to consider is how we detect client and server shutdown, because we don't want to be spinning infinitely if either the client or the server shuts down. If the client shuts down and there's the server is a dedicated server, the server should shut down. The other hand, if it's a multi-threaded server that can handle multiple clients, the server should not shut down, but the server thread handling the client should shut down. On the client side, if the server shuts down, the client shouldn't sit there endlessly, but also should shut down. So this is how you can do it. So you can detect when a shutdown has occurred when the socket read object returns null. And that will happen soon as the socket on the other side of the communication link ends. So if I'm on the client side and the server shuts down, the server's socket immediately sends a null to the client side, which will be read immediately, and we can fall out of the loop and terminate. One important thing is not to get suckered into thinking that if you close the socket on the other end, that will somehow signal us that that process terminated. It does not. You will sit there and hang because for whatever reason, Java's designers did not have socket close signal the other party in the communication that it was hanging up. Now in the server thread, it's very easy. If we're a dedicated server thread to that client, we simply exit the while loop, we wrap up our processing, and we terminate. For the client, if it's multi-threaded, detecting shutdown is a little more difficult. In the example I gave with the chat room, it will be the write console thread that actually is notified that the server shut down. And that is because the socket's read object will return null and while is going to get out of there. So what it needs to do after it has exited the while loop, it needs to somehow notify the main thread of the server shutdown. And the way that I've done that is to define a Boolean variable in the main thread called interrupted. And it needs to indicate, the write console thread needs to set interrupted to true. Now over here, because reading from standard in is not an operation that will throw an interrupted exception, we're not going to immediately exit. However, if the user gets tired or wonders why something hasn't happened and tries to enter something, at that point, there will be data coming in from standard in. Before it tries to process that data and write it to the socket, it should check to see if it's been interrupted, if the interrupted flag has been set to true. And if so, it should now break out of the loop, and that will shut down the client side.